Hi everyone, and welcome to our second tutorial. In this tutorial we're going to continue our discussion of the normal distribution from last tutorial, and we're also going to introduce the central limit theorem and the sampling distribution. Before we get started, I just want to tell you a hint about Mike's YouTube videos. So if you click on the Show More tab below each video description, you can then click on timestamps to the left to jump to different parts of the video that you're interested in. So for example, with this video on box plots, you could click the timestamp at the bottom if you want to learn how to report the minimum, first quartile, medium, third quartile, or maximum in a box plot using R. I also just want to flag this video that Mike has on his YouTube page. It's under the Fun Stats Concepts video series, and it introduces the concept of a sampling distribution with Mike as a puppet. So you might want to check that out if you haven't already. So as I mentioned in the last tutorial, the normal distribution is appropriate for summarizing continuous numeric variables. It's bell-shaped and symmetrical around the mean, and it's defined by two parameters, the mean and the standard deviation, with the spread of the distribution determined by the standard deviation that surrounds the mean. We also talked about how the total area under the curve is 100% and follows the 68, 95, 99.7 rule. So approximately 68% of the data will be within plus or minus 1 standard deviation of the mean. 95% of the data will be within plus or minus 2 standard deviations of the mean. And then 99.7% of the data will be within plus or minus 3 standard deviations of the mean. This rule is also important because we know that only about 5% of values will be more than 2 standard deviations away from the mean. And it's extremely rare that we'll observe a value that is more than 3 standard deviations away from its mean. To compare two observations or individual values that come from the same or different distributions, we can do what we call standardizing, which we discussed in the last tutorial. So what standardizing does is change the values of a variable so that the mean now equals 0 and the standard deviation equals 1. So once we standardize, the values of the variable now tell us how far each observation is in terms of its standard deviation, or the average amount that observations vary from the mean. And this is useful because it tells us if our data point x is expected or unexpected. So here's an example problem. The IQs of high school students follow a normal distribution with a mean of 90 and a standard deviation of 18. What is the probability that a randomly selected student has an IQ above 115? What's the probability that a randomly selected student has an IQ between 85 and 115? And what is the minimum score needed to have an IQ in the top 10%? So we write out all our knowns. And so we're interested in the area of the distribution above 115 for our first part of our question. We know the mean is 90 and the standard deviation is 18. So we plug all of this information into our formula to calculate a z-score. And this gives us a z-score of 1.34. So we then look it up in our z-table and see that with a z-score of 1.34, 9.01% of the distribution is above this score of 1.34. So the probability that a randomly selected student has an IQ above 115 is approximately 9%. Part B asks, what's the probability that a randomly selected student has an IQ between 85 and 115? So we already know the percent of the distribution above a score of 115, but now we need to calculate the percent of the distribution below a score of 85. So again, we plug this into our z-score formula and find that this equals negative 0.28. So we look this up in a z-table, which shows us that the percent of the distribution below a score of negative 0.28 is 0.3897. We now take both of the percentages we calculated that are in the tails, or outside of 85 and 115, and subtract these from 1, or 100%. And we're given our answer of 52.02%. So we conclude that the probability that a randomly selected student has an IQ between 85 and 115 is 52.02%. Part C asked, what is the minimum score needed to have an IQ in the top 10%? So we write out all our knowns, and we're interested in the score associated with the 90th percentile. So the first thing we want to do is determine the z-score associated with the 90th percentile. And afterwards, we'll use our z-score formula to turn this into a raw IQ score. So we look up the z-score associated with the 90th percentile in our z-table, and we can see that this gives us a z-score of 1.28. So in other words, 90% of the scores in a normal distribution are below a z-score of 1.28. Alternatively, we could use our second type of z-table and look for the z-score associated with 10% of the distribution in the tail, which is also 1.28. So the next thing we do is plug in this 1.28 z value into our z-score formula. And then we solve for x. And this gives us a raw IQ score of 113.04. So we conclude that an IQ of 113.04 is needed to have an IQ in the top 10%. So now we'll talk a little bit about the central limit theorem. So having a strong understanding of this is really fundamental to your continued learning in this course. So it can be a tricky concept, but I suggest that you take the time to read over this in the Module 2 notes until you feel really comfortable with it. So the assumptions of the central limit theorem are that all observations are independent of one another and randomly obtained, as when you collect a simple random sample. So independent means that the selection of each participant does not affect selection of another participant, and obtained randomly means that every participant or observation has an equal probability of being selected. The central limit theorem says that when these two criteria are fulfilled and the n is large enough, the sample mean and sample sum will approximately follow a normal distribution. This is the case regardless of what kind of distribution our random sample comes from. The more symmetric and light-tailed the distribution, the quicker that the sample mean and sample sum will converge to normality. The more skewed the distribution, the larger our sample needs to be. So a sample size of 50 is usually adequate for fairly skewed distributions. But provided that the distribution is not too skewed or asymmetric, a sample size of 20 is usually adequate for the central limit theorem to work. There's a really good example in Module 2 from page 55 to 60 that shows how the central limit theorem works and what it does and does not apply to. So you might want to go over this a few times to help solidify concepts. So I'll just walk you through a little bit of an example to distinguish between the ideas of the distribution of a sample and the sampling distribution, and to learn about the central limit theorem. So let's assume we have this population. This is what's actually happening in reality, the truth. So let's say we take a simple random sample of 50, and then we take many more samples of 50. Now looking at each of these samples one at a time, we can calculate a sample statistic. For example, we might calculate the average age in each sample to get our sample mean age. This would be our sample statistic in this case. So let's say we do this for each of our samples, and then we have a sample statistic like mean age that arises from each of the samples. We would expect these sample statistics to be similar to each other, but we would not expect them to be the same across each sample. So then, if we plotted all the mean ages from each of the samples, this plot is what's known as the sampling distribution of the sample means. On the other hand, the distribution of observations, so the individual ages of 50 different people in each sample, is what we call the distribution of a sample. These concepts sound the same, but are very different. The central limit theorem does not apply to individual samples. So for example, let's say a population distribution of ages is highly skewed. So let's say very few people are below the age 40 and most of the population is above age 65 and 25% is above age 80. When we take a sample of individuals from this group and plot the distribution of individual ages, this should not look normal. We would expect this to also look skewed. On the other hand, if we take many samples from a skewed distribution, calculate a mean for each of these samples, and then plot each of the sample means, the sampling distribution of the sample mean will approximately follow a normal distribution, as long as the assumptions listed on the previous slide are met. And the larger our sample size gets, the closer our sampling distribution of the sample mean will get to approximating a normal distribution. So let's take a look at an example. Let's say we're interested in the average annual income of recent graduates from business degree programs in Canada. So recent graduates from business programs is our population. Our parameter of interest is the average annual income. Let's assume we had income data from every single recent graduate of a business degree program in Canada. Even though that would mean that we wouldn't need to sample from the population because we would already have information on everyone, but let's just assume that we did have this data for the sake of this example. And using this data, we could find the population mean by adding up all the individual incomes and then dividing by the total population size. Let's say, for example, the average income is $50,000. So our true population mean is $50,000. And let's also say that our distribution of individual incomes is positively skewed, so that incomes tend to cluster around the lower end of our salary scale, and there are very few higher scores, as shown in the histogram here. We could then calculate the true population standard deviation, take all of the incomes in our population, plug it into our formula, and calculate the population standard deviation. This would tell us how far individual salary observations move from the true mean salary on average. For our population, we would expect that the standard deviation would be very large, since the salaries in our population are probably very variable. So for example, salaries would probably range from very low to very high. Now let's say we take a random sample of 500 recent graduates from each business degree program across Canada. So for example, I could start with UBC and plot the individual salaries as a histogram. This is the distribution of our sample. Note that we would not expect this to look normally distributed. We would expect this distribution of individual salaries to look positively skewed, like the distribution of the larger population of all Canadian university graduates. Using this data from UBC, I could calculate an average income for that sample. We would expect the mean income of the sample to be about $50,000, but we also know that it probably won't be exactly $50,000. It will likely vary a bit from this population average. And then I could go to hundreds of universities across Canada and calculate the mean incomes of graduates from each business degree program. So now our new data set consists of sample means, university averages. So instead of my data being individuals whose incomes I'm reporting, my data is actually sample statistics, or the mean income of recent graduates from each of these universities. If I plot all of these sample mean incomes on a histogram like the one shown here, this gives us the sampling distribution of our sample mean. And this is where the central limit theorem applies. Even though the distribution of the individual salary data is positively skewed in our population and in each sample, when we plot the means from each of these samples, we expect the sampling distribution of our sample means to be approximately normally distributed around the true population mean of $50,000, since we wouldn't expect the mean for each of our sample to be too far off the true mean salary. In other words, we expect the mean of the mean salaries from our samples to be $50,000, even though it may vary from this a bit. In reality, we usually are collecting only a single sample and calculating a single mean. When we do this, we expect our sample mean to equal the true mean of $50,000. But as I mentioned, we know that it will likely differ from this a bit. And we can actually quantify how much we expect our sample mean to vary from the true mean. It will vary from that expectation with a standard deviation of the true standard deviation divided by the square root of the sample size. This is what's known as the standard deviation of the sample mean. The standard deviation of the sample mean tells us, on average, how far the sample mean salary deviates from the mean of the means, or the true mean. We expect this value to be much lower than the population standard deviation of individual salaries, since we would expect the mean salary for each university to be pretty close to one another. So for example, we wouldn't expect to find a university where the average salary was as low as $10,000 or as high as $500,000, even though we might find these values if we were looking at individual observations in a single sample or in the larger population. So the variability of our sample means is going to be lower than the variability of individual salaries in our actual population. In fact, the standard deviation of the sample mean will decrease as the sample size increases, because, as I mentioned, this value is equal to the true standard deviation divided by the square root of the sample size. What this means is that the lower the number of business graduates we sample from each university, the more variable we would expect the sample means to be, and the higher we would expect our standard deviation of the sample means to be. So let's say we're selecting only a very small sample of 3 graduates from each university. It's possible that we sample someone who has a very high or a very low salary, and their salary is going to have a whole lot more bearing on that university sample's average. So if we plotted these salary means on a histogram, there would probably be a high degree of variability in these means, or a larger spread. On the other hand, if we sample 1,000 graduates from each university, that extremely high or low salary of an individual will have much less impact on our average salary. In this case, where we are sampling 1,000 graduates, the mean salaries are likely to be much closer to one another. The variability or spread of these mean salaries will be lower than the variability of mean salaries when we were only selecting 3 individuals from each university. In other words, our standard deviation of the sample mean is lower in this situation. So formally, the central limit theorem tells us that we can expect the sampling distribution of the sample mean to be approximately normal. No matter what distribution our random sample comes from, the sample mean will follow a normal distribution as long as certain conditions are met, that observations are independently and randomly sampled, and the sample size is sufficiently large. The central limit theorem also tells us that the mean salary of the sample means is expected to equal the true population mean salary, and the calculation of the standard deviation of the sample mean, that is, how far our sample mean deviates from the true mean, is the standard deviation of the population divided by the square root of our sample size. This is also sometimes referred to as the standard error. Something to keep in mind, though, is that the term standard error is defined as the sample standard deviation divided by the square root of the sample size. But often this is used interchangeably with this second formula, the true population standard deviation divided by the square root of the sample size. This second formula is known as the standard deviation of the sample mean. On average, how far will the sample mean move from the true mean? Even though the concept is the same, these two are slightly different. The standard error is used to describe the accuracy of a sample mean as an estimate of the population mean. It gives us an estimate of how close our sample mean is to the true mean value. It relies only on the information we have as part of our sample, in the situation where we do not know the true population parameters, which is most often the case. And this tells us how much our sample mean is likely to deviate from the true mean on average. On the other hand, with the standard deviation of the sample mean, you do know the population parameters. In other words, the standard error gives you an estimate of how close your sample mean is to the true population mean. The standard error is computed solely from sample attributes. We are using the sample as a representation of the population, so using the information from our sample to estimate the population parameter. The standard deviation of the sample mean shows you how much your sample differs from what you know the true population mean to be. The standard deviation of the sample mean cannot be computed solely from sample attributes. It requires knowledge of one or more population parameters, for example, the population mean. So this slide is just a brief summary of the differences between a distribution of a sample and the sampling distribution of the mean. We've already gone over this quite a bit, but this is a really important part of the course. So the unit of a distribution of a sample is an individual observation. The mean is defined by x bar. So using our previous example, this would refer to the mean salary in a sample. The standard deviation of our sample is defined as the average deviation of the individual observations from the mean, or how much individual salaries deviate on average from the mean salary in a sample. As our sample size gets larger, our sample estimates get closer and closer to the true values, or the population values. This does not mean that this will follow a normal distribution. If the distribution of our data in a population is skewed, and we take a sample from that population, we are likely going to have a skewed distribution as well. On the other hand, with the sampling distribution of the mean, our unit is the mean of each sample. We expect to get a sample mean that equals the true mean, but know that our sample mean will likely vary from this a bit. It will vary from that expectation with a standard deviation of the true standard deviation divided by the square root of the sample size. And with the sampling distribution of the mean, as our sample size gets larger, the sampling distribution of the sample mean will become closer and closer to approximating a normal distribution, regardless of the distribution of the individual data in our population. Okay, so now let's turn to an example problem. Suppose it is known that for high school students, the true population mean IQ is 90 with a known standard deviation of 18. Researchers randomly select 30 people from this population. What is the probability that the sample mean IQ is less than 84? What is the probability that the sample mean IQ is more than 5 points away from the true mean? Note the distinction here compared to the earlier practice question is that with this question, we are asking about the sample mean in relation to the true mean. But with the previous practice question, we are asking about a randomly selected single student, what's known as an individual observation in relation to the true mean. This distinction is very important in determining how we should calculate z-scores and associated probabilities. Since we have a large sample size and our observations were independently and randomly obtained, we know that our sample mean will approximately follow a normal distribution with an expected value of 90. We also know that the standard deviation of the sample mean equals the population standard deviation divided by the square root of the sample size, or 18 divided by the square root of 30, which equals 3.286. If we say this in notation, it looks like this. This is the sampling distribution of our sample mean. It is the distribution of all possible sample means that we may get when we take a sample of 30. For the first question, we want to know the probability that the sample mean IQ is less than 84. To do this, we first standardize the value of 84. So 84 minus 90 divided by 3.286 equals negative 1.83. So getting a sample mean of 84 is 1.83 standard deviations below what we would expect the sample mean to be, the true mean of 90. What is the probability of obtaining a sample mean that is 1.83 standard deviations below the true mean or less? To figure this out, we turn to our normal table, or we can also use software. Here we find that a z-score of negative 1.83 is associated with a probability of 0.0336. So we conclude that the probability that the sample mean IQ is less than 84 is 3.36. Okay, so now let's turn to part 2 of the problem. What is the probability that the sample mean IQ is more than 5 points away from the true mean? More than 5 points away, meaning 5 points in either direction of the mean, so either below 85 or above 95. So if we first start with 85 and follow the same process that we did previously, we get a z-score of negative 1.52. So getting a sample mean of 85 is 1.52 standard deviations below the true mean, or 1.52 standard deviations below what we would expect the sample mean to be. If we then look at our z-table, we see that the probability of the sample mean being in the tail below a z-score of negative 1.52 is 0.0643. So there's a 6.43% probability that the sample mean IQ is below 85. We know that since 95 is the same distance away from the true mean as 85, the z-score associated with 95 will be the same as with 85, except that it will be a positive value rather than a negative z-score this time. So there's a 6.43% probability that the sample mean IQ will be above 95. The next step is that we add the probability of obtaining a sample mean below 85 and the probability of obtaining a sample mean above 95. And this gives us 12.86%. So we conclude that the probability that the sample mean IQ is more than 5 points away from the true mean of 90 is 12.86%. Here's a final example problem for this tutorial. So use the following data to answer the question below. Data are from SPPH for 100 students resting pulse rate. The resting rates are as follows. Compute the mean, median, range, and interquartile range. Draw a box plot, and draw a box plot where 84 is replaced with 100. Try this in R and then try it by hand. So the score at the bottom is the minimum, which equals 68. The maximum is the score at the top, which equals 84. So the range is from 68 to 84. So 16 is the range. The middle score is the median, which equals 76. The mean, the average of all the scores, is also 76. And the edges of the box are the first quartile and third quartile. So the first quartile equals 73, and the third quartile equals 79. The interquartile range is calculated by subtracting the first quartile from the third quartile. So 79 minus 73 equals 6. When 84 is replaced by 100, the minimum obviously stays the same at 68. The maximum is now 100. The range is now from 68 to 100, so 32. The median stays the same at 76 because it's still the middle value, so 50% of the scores are still above and below this point. But the mean has moved up from 76 to 78.6 because this has been pulled up by replacing 84 with the outlier of 100. But our interquartile range stays the same. The 50% of the scores in the middle have not changed. So the first quartile is still 73 and the third quartile is still 79. So the code is shown here on how to do this in R, and I also encourage you to try this by yourself by hand. For our next tutorial, we're going to discuss the difference between Z statistics and T statistics. We'll also introduce confidence intervals, including how these are calculated and their assumptions. We'll discuss the margin of error and how we can influence this as researchers. And we'll also cover the difference between one- and two-sided confidence intervals.